Hello, everybody. Welcome to a demo of the application lifecycle management across multiple edge clusters. We will demonstrate the deployment of an application and its migration from one edge cluster to another while preserving service continuity. This is a collaboration between Intel and Orange. We will introduce you to the Edge Multi Cluster Orchestrator, also known as MCO, and the temporal workflow engine, and then describe how they work together. We will then explain the demo scenario and setup, and then proceed to the demo. The rise of multi-access edge computing, or MEC, poses the challenge of deploying cloud-native applications at scale across geographies among a large number of MEC clusters. Intel designed MCO to address these challenges and donated it to Linux Foundation. MCO orchestrates services and resources in Kubernetes clusters using an intent-based declarative approach. It can handle clusters in telco edges, enterprise edges, public and private clouds, and also on on-prem data centers. Its core functionality can be extended using new controllers. A significant new enhancement to MCO in the latest release is the ability to launch and manage workflows. Workflows are complex sequences of tasks, each of which may potentially fail, but the sequence needs to be completed reliably. Many complex edge computing scenarios require custom workflows, so this makes MCO significantly more extensible. While Intel developed the core feature, Orange has contributed the edge relocation workflow that we'll demonstrate today. There are many scenarios that need workflows. For example, say an user element or UE is communicating with an application in a MEC cluster. The UE may roam to a new cell tower where another MEC cluster is closer. We may want to migrate the application to the closer cluster to reduce latency. MCO can handle workflows using the temporal workflow engine. It is an open source engine that offers resilience and proven scale. This does not preclude MCO integration with other workflow engines in the future. A temporal deployment consists of a temporal server, a set of workers which run in containers in a cloud-native scenario, and workflows which are custom application code executed by the workers. The workflow client, which starts and manages workflows, also runs custom code. MCO can accept workflow intents via APIs, launch workflows by invoking workflow clients, monitor, query, and cancel workflows via the temporal server. By running workflows from MCO instead of directly, workflows can be executed in multiple edge or cloud clusters, and the user gets a single dashboard for orchestrating applications, network functions, and workflows. To understand how MCO works with temporal, let's say a temporal server is running in a cloud. The workers may be running in containers, maybe in a different cluster. The workflow clients also execute in containers, possibly in a remote cluster. MCO's microservices may be deployed in some other Kubernetes cluster fronted by an API gateway. The newly added workflow manager service in MCO accepts workflow intents from the user and invokes the workflow by calling the workflow client. This requires that the workflow client should expose a simple REST API to pass the workflow client name, workflow parameters, and options like timeouts. MCO's workflow manager can also directly talk to the temporal server for monitoring and canceling workflows. The demo scenario involves two geographically distributed edge clusters, plus several other components residing in various Kubernetes clusters, including MCO, the workflow components, and the temporal server. The mobile UE is running in a client which fetches images from an image server. The Power DNS resolves the name lookups from the image client. At the start of the demo, all these components are up and running. The workflow components may have been deployed by MCO itself. In step one, MCO deploys the image server application in cluster 1. This triggers an automatic update of the DNS entry for the image server in Power DNS. When the client starts to connect to the server, it first resolves the server name via DNS. Then the client starts to fetch images once every few seconds from the server. Say the client starts to roam now and moves to a different cell tower where cluster B is closer. Okay, this should trigger a migration of the image server to cluster 2 to be closer to the UV. In this demo, we do it manually, but we want to automate it later. This again triggers an automatic update of the DNS entry for the image server in Power DNS. And finally, the client can query the DNS and start traffic to server in cluster 2. Since there are numerous clusters and components in the demo scenario, for demo purposes, we have consolidated them in just 2 clusters and a few hosts. The deploy server houses the Git repos for MCO and the workflows, and also the temporal server. Cluster 1 has MCO and the workflow components in different namespaces. MCO deploys the image server in cluster 1 initially, and then it is migrated to cluster 2. Each cluster has external DNS, which is an open source component to publish cluster services externally in Power DNS. We can learn more about MCO, and we invite you to contribute to MCO. Let's now start the demo. We have opened terminals to the 5 major components of the demo in the top right corner. Cluster 1 is a single node cluster, and it's got an IP address of 192.168.135. It is currently running the external DNS and the MCO monitor. In addition, in the demo namespace, it is running the workflow client and the worker. And in the MCO namespace, you can see that the MCO microservice already been deployed. Cluster 2 is also a single node cluster. Its node is on a different subnet, and its IP address is .2.191, and it is running the external DNS and the MCO monitor, but nothing else. Power DNS is running in a separate node, and it's been configured with a DNS zone called demo.com. Right now, only the zone record exists in Power DNS. There is no host record of type A for any host yet. You'll eventually deploy imageserver.demo.com in this Power DNS. On the bottom right side, we have the node which houses the Git repositories and runs the temporal server. We'll use it to issue the MCO commands. And finally, in the bottom left side, we have the node which represents the mobile UV where the image client is running. We will first start the demo by deploying the image server application in cluster 1. This final command instantiates the image server in cluster 1. You can see that it's running in cluster 1 as a node port service exposed in port 32000. Cluster 2 does not have any image server yet, and Power DNS has been updated with the A record for imageserver.demo.com with cluster 1's IP. So with this background, we should be able to start the image client. But before doing that, I'm first going to define the workflow intent, so it'll be easier to show the migration later. So coming to this image client terminal, I'm going to start the image client. And you will see that it is fetching the image every few seconds from the image server. Okay, and it's getting it from .1.35 because that's what Power DNS indicates. We will now start the workflow. And we can see that it seamlessly picked from cluster 2 because Power DNS has been updated to point to cluster 2. And now you can see that cluster 2 is running the image server with the same node port as before. And cluster 1 is not running the image server anymore. So with this background, let's try to see what happens if we try to relocate the image server back to cluster 1. So when we do that, we will see that it picks up from cluster 1 again, which is because Power DNS got updated once more to point imageserver.demo.com back to cluster 1. Cluster 2 is not running the image server anymore, and cluster 1 is running the image server again. So this shows that we can seamlessly migrate applications from one edge cluster to another in response to a simulated event of UV migration. Thank you.